Today, guys, our goal is to wrap up everything we've been learning about this unit on thermochemistry. We're going to be talking about phase change and being able to calculate the energy associated with phase change. And this is going to pull together everything we've been talking about. States of matter, kinetic molecular theory, specific heat, heat capacity, joules, calorie. This is where it all gets tied together. So hopefully after this podcast, you'll kind of see how all these connect together and why we've been talking them. So let's go ahead and get started. Okay, first of all, let's just kind of review what a phase change is. All it is a change in matter from one state to another. For example, if we talk about water, it starts as an ice cube. We add some heat, it turns to water. Add more heat, it turns to water vapor. We could also go the opposite way if we cool things down. We can start with steam, cool it down to liquid, and then freeze that into a solid. So phase change works either way, either adding energy or taking energy away. But that's the big thing you got to realize, that any change in phase requires a change of energy within that matter. We have to either be speeding those molecules up so they're moving faster, or cooling them down so they're not moving as fast. And that's the whole idea with phase change. Okay, this energy that we add or take away, or that we add in this case, is used to break those intermolecular forces that hold the molecules together. As we reduce energy, reduce temperature, those intermolecular bonds reform and hold things together. Okay, so let's talk about a couple basic types of phase changes. You're probably familiar with these already, but we're going to go ahead and put some words to them, or names. Vaporization. Think about something becoming a vapor. All it is a change of phase from liquid to gas. Okay, and this occurs at the boiling point, the temperature at which boiling occurs. Think about boiling water, right? Well, what's happening when you're boiling water? You're taking from a liquid to a gas. Now, if we go in the other direction, from a gas to a liquid, we're condensating. Okay, we have condensation going on. Okay, so the condensation point is the temperature at which this condensation occurs. An example of condensation: when you're taking a shower and water droplets condense on a mirror, on a glass surface. That's an example of it. Okay, another phase change is what we call sublimation. Sublimation is unique because it's a change of a phase directly from a solid to a gas. It doesn't go through the liquid stage. Best one that you guys are probably familiar with is dry ice. Think about dry ice, right? You have a block of it and all of a sudden it vaporizes directly into a cloud. Okay, another one you probably don't know is iodine. Iodine will do this well. We can see in this picture here, iodine, when it's heated, goes from a solid state up to a gaseous state. You got to be careful though, because the iodine vapor is toxic. Now, there is an opposite of this as well, and we call that deposition. And this is a change directly from a gas to a solid. And I know all of you have seen this. You just don't know what it is. Frost. You come out of your house, go to a car in a cold morning that's been sitting out, you have frost. Well, if you were to watch that, the frost you never got liquid on there first. It directly went from water vapor in the air to a solid form, frost, on your windshield. So the first thing we need to do when we start looking at this is create a heating curve. And here is a generic heating curve. This could be for any substance. The only thing that's going to be different about these from one substance to the other is the temperature at this line and this line. Here's our melting, freezing. Here's our boiling or vaporization, condensation point. And we'll put those temperatures here. We have temperature here and we have heat there. Okay? These diagonal parts represent the three phases of matter. We have solid down here with the least energy, a little more energy. We have liquid, and then finally gas. So the diagonals represent a single state. These are all solids, these are liquid, these are gas. Now these plateau areas, these flats, are going to represent our phase change. So we're going from a solid to a liquid, we're melting. If we go the other way, a liquid to a solid, we're freezing. Think about water. Okay, that's the easiest way to put these in there. You're all familiar with water. Okay, so on this plateau here, we have a solid and liquid, right? When a ice cube starts to melt, it doesn't all instantaneously melt, right? You have some solid and you have liquid. So it's a solid and liquid both existing. Now this upper phase, when we go from a liquid to a gas, we call it vaporization. Okay, when we go from a gas to a liquid, we have condensation. So on this plateau, we have both liquid and gas. I would pause the video here and copy this down. We're going to add a couple more things to it, but it's really important. So pause this, Once you're done copying this down, come back and we'll go on to the next slide. Okay, here's just a slightly different version of it, and I put it in these 4 points, and we talked about these already. Down below here we have the melting point. This is where it starts to melt, okay, solid to liquid. Over here we're going from a liquid to solid, so we're starting to freeze. That's our freezing point. And look, the freezing point and melting point are the same temperature, and this is for water, right, because we're at 0 degrees. So melting point and freezing point are same temperature, it just depends what we're doing. Now up high here we have the boiling point here. This is where it starts to boil. If we're going from a vapor or gas to a liquid, we have what we call the condensation point, where it starts to condense. Okay, once again, boiling point and condensation point are the same. For water, it's 100 degrees. It's really important that you put the boiling point and melting point in, because for each different substance, it's going to have a different boiling and melting point, and it's going to help you with your calculations later. That way you don't always assume it's 0 and 100. That's only for water. Okay, the whole idea behind this, or for the phases, is the intermolecular forces. So as the amount of energy and the temperature in the molecules increase, they're able to overcome these intermolecular forces and pull farther apart, and that's what allows them to start moving and start changing phases. Okay, so if we add enough energy, we break enough of these intermolecular bonds, well, phase change occurs. On the graph, this phase change is occurring in this plateau area. Remember, here's our graph again. Here's our phase change, and here's our phase change. So we notice right here, or let's look at the diagonals first. Here we're increasing temperature, right? But when we get to these phase change, we're not increasing temperature anymore. The temperature is staying the same, but look at this. The heat energy is still increasing. Well, why is that? Well, the question is, what's going on in those? We're not changing temperature. Instead, at these plateaus, the energy is going into breaking those intermolecular bonds. Okay, we're not trying to raise temperature here. We're changing phase. So in the plateau, we're not changing temperature. We're breaking those intermolecular bonds so we can switch from a different phase. Okay, so the couple values we need to talk about. The heat of fusion is the energy required to change 1 gram of solid to a liquid. So that's that bottom plateau. How much energy is to change 1 gram to a liquid? Okay, and then the opposite, if we're going from a liquid to a solid, it's the energy release, exothermic, right? Energy given off when 1 gram of substance changes from a liquid to a solid. So both of these are the same value. They're just running in opposite directions. Okay, kind of like melting and freezing. The same temperature, different processes. So make sure you get these down. Now, these are specific values. I will always give you these values. I'm going to have you copy the heat of fusion value for water down, so you'll have it when you do practice problems. But in a test, I won't expect you to memorize that. I will give it to you. Now, if we look at the upper plateau, we have the heat of vaporization. Vapor, we're making vapor from a liquid, so it's the energy required to change 1 gram of a liquid into a gas. The opposite of that then is heat of condensation. Energy release given off when 1 gram of substance changes from a gas to liquid. Once again, these are the same numerical value. They're just working in opposite directions. So be aware of that. Okay, let's talk about then, how do we do phase change calculations? How do we calculate how much energy is required to do something? So what we're going to talk about are stages in the phase change. What's happening? Is it heating up? Is it changing phase? Is it then heating up again? So for each stage that we go through, there is going to be a calculation. Okay, 2 things. If we think back to that plateau, or excuse me, that heating curve are happening. Either you're heating up, those were our angles, right? We had 3 angles where it's a single state of matter, solid, liquid, or gas. Okay, or well, if we heat it up, we're going to use our heat energy. Remember this equation? Heat energy is specific heat times mass times delta T. Well, that's our angles. The other thing we can do is what I call break it down. This is the phase change. We're going from one phase to another. And our formula for that is we're going to take the mass of whatever we're doing, using, multiply by the heat of fusion, heat of vaporization, heat of condensation, whatever that value is at what plateau. So let's go ahead and take a look at some of these here. So here's our basic phase change diagram. Every time you do a problem, I would quickly sketch this out. Okay, Make sure you put the numerical value of the melting point and the boiling point here. And then here are our different phase stages. Here's a stage. So each line represents a stage. Okay, here's a stage. Here's stage. Here's stage. Here's stage. Here's stage. The diagonals then represent we're heating it up versus the plateaus where we are breaking it down. So we have two places we break it down, one here, and there are three heating up. Three sections where we heat it up. So we're going to have two equations that we use. Okay, so copy these energy values down. Like I said, you're going to use these a lot, so it's good to have them written down somewhere where you can look at them closely. On a test, I will give you the first two. Heat of fusion. Okay, remember that's low, our melting point there. It's 334.72 joules per gram. So it takes that many joules to melt 1 gram. Now, if we go up to heat of vaporization, we got 2259.36 joules per gram. So it takes a tremendously amount more of energy to change something from a liquid to a gas than it does from a solid to a gas. Excuse me, solid to a liquid. This is why steam burns are so bad. There's so much energy contained in that steam as compared to if you just grabbed something that's 100 degrees versus getting steam on you that's 100 degrees. There's so much more energy. Then the other value that you already know that you still need to know, because I won't give it to you, is the specific heat of water, 4.184 joules per gram degrees Celsius. So make sure you copy these down. Okay, let's do an example problem together. It may look something like this. How much energy is required to melt 25 grams of ice that is at 0 degrees Celsius? So first thing I'm going to do is I'm going to create my generic phase change diagram. It says it's water. I know it's 0 degrees for melting, 0 degrees for freezing and melting, and then 100 degrees for boiling point. Now, first thing I got to determine is where am I starting? Okay. Well, it says I'm at ice at 0 degrees. Well, here's 0 degrees. Is it here or is it here? Well, here's my solid, so I'm starting right there. Okay. Then I want to melt it. Okay, I want to make it to liquid water at 0 degrees. So I'm going to end here. So all I'm doing is going through a plateau, right? And that plateau is going to be a break it down equation. Okay, so there's my question again. So I'm going to use the phase change equation to break it down. Remember that was mass times the heat of, in this case, it's going to be heat of fusion. So I take 25 grams, which is given, times the heat of fusion, 334.72 joules per gram, and I end up with 8,368.00, don't forget 2 decimal places, joules. So it takes that much energy to melt 25 grams of ice. Change a 25 gram ice cube to water. Okay, let's try a little more complex one now. How much heat energy is required to vaporize 35 grams of water that is presently at 50 degrees. Well, what's vaporize mean? Well, that's a change in state from a liquid to a gas. So I'm going to draw my diagram here. It's water, so 0 and 100 again. Where am I starting? Well, I'm going to start at 50 degrees Celsius. That's somewhere right there. And I want to completely vaporize this, which means it all wants to be a gas form, so I'm going to end there. So I'm going through two stages. I'm going to heat it up for stage 1, and then I'm going to break it down. So this is going to have two calculations on it. Let's look at what those would look like. And I like to set these up using our factor labeling table. So I'm going to start with specific heat, our mass times specific heat times delta T. Remember, it's our equation for heating it up. So 35 grams, specific heat of water, 4.184 joules. And then my temperature change. Well, I'm starting at 50. I know the boiling point is 100. So my difference between 150 is 50 degrees. That's delta T. This is where it becomes really important that we put our temperatures in. Because if you always assume it's 0 and 100, you're going to get those numbers wrong. So I do my multiplications. I end up with joules, right? I end up with joules. Grams cancel here, Celsius there, left with joules. So that's, I heat it up. Now I have to change the phase. And that's mass times the heat of equation, right? So 35 grams times 2259.36 joules. I gave you that value. Okay, now to get the total energy, I have to add these two together. So I get 86,399.60 joules. That's how much energy is required to change 35 grams of water at 50 degrees to water vapor at 100 degrees. All right, I want you to try this one on your own here. Go ahead, copy this down, and then once you get copied down, work it out, and then come back and check the solution. Now, if you don't have your calculator with you right now, that's okay. Go ahead and set up the problem. We can figure out the actual answers later, but the setup is really important. Please note here, we're going to express your answer in kilocalories, not joules, so don't miss that. So pause me, copy this down, work it out, and then come back. Don't cheat, do it. Alright guys, so here you are. Here is our generic heat grid, and it's for water, so it's 0 and 100 for melting and boiling point. So where are we starting? We're starting here at -4, and I want to go all the way up to, I think it was 115 degrees. So how many phases do I have? I have 1, 2, 3, 4, and then 5. So you're actually going to have 5 calculations to do. So it's a bit of work on this one. So let's look at each stage. Each stage, first stage I had to go from -4 to 0. So that's a heat energy, 35 grams times specific heat times 4 degrees gives me that value. Now I have to melt it. So it's your mass times your heat of fusion or heat of vaporization, whatever value we're doing. Okay. So 35 grams times 334.72 gives us that. Now I'm at liquid at 0 degrees. I got to get liquid to 100 degrees. So once again, heated up equation. Delta T in this case is 100 degrees. Okay. Now I have to go from liquid to vapor. So mass times your heat of value. I come up with that. And then final stage, I have to go from gas at 100 degrees to gas at 150. So we're going to heat it up once again. Okay, so this should be your setup right now. Now to get the total energy, we'll add these up. Here's a little side note. Okay, we've been using this value right here for our specific heat of water. We're going to stick with that. In reality, what we see, water has a slightly different specific heat in each phase in solid, liquid, and gas. I have a slightly different one, but just to keep things simple for us, we're going to use this 4.184 joule value the entire time. Please know it's not 100% accurate and that it's actually different for solid, liquid, and gas, but for our sake, we're going to leave it that. Okay, so now I have all these values. I'm going to go ahead and add these up, okay, and I get a big number, okay, but it's in joules. We want it in kilojoule or kilocalories. Now remember, there is no direct conversion between joules and kilocalories. I got to go to calories first. So think back to what you learned. I start with my given there. I know that 1 calorie is equal to 4.184 joules. My joules cancel, and that 1 kilocalorie is equal to 1,000 calories. Remember, kilocalories and big C calories are the same thing. So now I do my math on here and I end up with 25.87 kcals. Now think about that in terms of food, right? That's 25.87 food calories. How much is that? Maybe 3 or 4 jelly beans. Oh, maybe, let's see, a can of soda typically has 250 calories, so a tenth of a soda, maybe an ounce. So in reality, when we talk about our body, that's not a lot of energy. But as far as phase changes, it's a significant amount. Okay, here is your homework. I want you to try these 3 problems on your own. Pause this and write them down and then go to the last slide. But we're going to come in class and work these on the board. Once again, extra points for whoever reminds me that we need to do these, because I will forget. But we want to work these out on the board. So copy them down here, practice them, and then if you want extra help, come in and see me before class so you can make sure you understand it. Alright guys, in this episode, hopefully we tied everything we've been talking about in the previous podcast for this unit together. We now know how to do calculations, how to calculate how much energy it's required to not only change the phase of something, but also to heat it up. And that if we're going from a solid all the way up to gas, that the total energy is a combination of the amount of energy required to heat it up and also to change phases. Okay, so make sure you have those 2 equations down, the heat it up and break it down equation, because I'm not going to give those to you on a test. You're going to be held responsible for those. So as always guys, if you have any questions on this or how to do any of this, please come see me before class, or make sure you're writing questions down as you go along. That way if you have any questions, You can just look down. You don't have to rely on your memory to re-ask those. Okay, guys, until I see you in next class, take care, and we'll see you soon.